Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Human civilization has been very lucky. At least most of us have been. The Clovis people are identified by a special type of spearhead they produced. These are called Clovis points. Somewhere between 40 and 20,000 years ago, the Clovis people migrated out of what is now western Alaska, down into North America. There they flourished, and by 13,500 years ago, signs of their civilization could be found all over North America. But then 12,800 years ago, they all vanished from the paleoanthropological record. It is probably not a coincidence that right around the same time, a large impact struck what is now the nation of Greenland, leaving a crater over 30 kilometers wide and blasting billions of tons of rock into the air, most of which would have come back down around the Earth, lighting up the skies and heating the atmosphere. Over 28 deposits of platinum around the world are indicated to have come from this impact site, showing that this was a metal-rich M-type asteroid, similar to, but certainly much smaller than, the bare core of a protoplanet that we call Psyche. These secondary impacts would have produced massive shock waves, resulting in tsunamis and firestorms, as well as putting enough dust into the atmosphere to darken the skies and bring about the equivalent of a nuclear winter. This worldwide catastrophe wiped out many species, almost certainly including this early human civilization in the Americas that we call Clovis. There is absolutely nothing in existence today keeping this from happening to us. We are trusting blind luck. The Earth received a warning in 1908 when a 12-megaton explosion from an incoming asteroid or comet flattened over 2,000 square kilometers in Tunguska, Siberia, and another in Chelyabinsk, Russia in 2013, when a meteor exploded with a force equal to about 500 kilotons, or 25 times the power of the American bombs used against Japan. This injured over 1,200 people because it exploded high in the air. In the movies about asteroid impacts, humans always have the time to build massive spaceships to intercept and destroy the incoming asteroid. But today, in the real world, we have nothing to defend us from this threat. The first step in developing a planetary defense force is determining the best way to change the path of an incoming threat. To do that, we need to hit one with a kinetic impactor, so we can study the impact explosion and see how much we can deflect an asteroid. To accomplish this first step, NASA has dedicated the resources necessary to slam a high-speed asteroid impactor called DART into a small, distant asteroid. The DART impactor left the Earth on a Falcon 9 rocket from Vandenberg Air Force Base on the 23rd of November, 2021. It has spent the last year traveling to its distant target and should impact on September 26, 2022. Let's review this mission. Then we'll see how NASA plans to observe the effects of the impact. The DART impactor will strike a small asteroid, orbiting a larger one, far away from Earth. This mission is called the Double Asteroid Redirection Test. Let's take a look at kinetic impactors. Please don't forget to like and subscribe, and help us out on Patreon if you can. We appreciate you. DART is a real kinetic impactor spacecraft, ready to launch into space later this year. The target is a binary asteroid called Didymus. The two asteroids orbit each other every 12 hours and are tidally locked. Didymus was discovered in 1996 by Joe Montani of Spacewatch. Binary asteroids are not uncommon. These occur when two asteroids come close enough to start orbiting each other. This causes both asteroids to orbit about the center of mass between the two. Both asteroids making up Didymus have a combined mass of almost 528 billion kilograms. Can I say teragrams? No? Fine. Billion kilograms. These asteroids have a density of 1.7 grams per cubic centimeter. Earth has a density of about 5.5 grams per cubic centimeter, and ice has a density of 0.92 grams per cubic centimeter. If we look at what we know about the asteroids, we can estimate their individual masses. These asteroids have been visualized with radar from Arecibo, with a wavelength of 12.6 centimeters, and confirmed by the Goldstone Radio Observatory at 3.5 centimeters. This is an actual image, with each pixel being 15 meters across. Here you can see an equatorial bulge. It is not uncommon for these to develop when an asteroid is composed of smaller pieces that can shift when it's spinning. These asteroids have a similar albedo, at about 0.15 optical. If you saw the lesson on the James Webb Space Telescope, you will recognize this as the same albedo as Mars. They are reflecting back about 15% of the light directed at them. These asteroids having a similar albedo means they should have similar compositions. The diameters are 160 meters and 780 meters. That gives us a radius of 80 meters and 390 meters, respectively. We know that the volume of a sphere is calculated with the formula 4/3 pi r cubed. These are not exact spheres, but close enough to give us an estimate. Pulling our numbers into the equation gives us 2.1 million and 248.5 million cubic meters, respectively. This means the smaller asteroid is less than 1% the volume of the larger one. If density is the same for these two, that would give the smaller one a mass of about 4.5 billion kilograms, of the total 528 billion. Didymus has a perihelion of a little more than 1 astronomical unit, and an aphelion, or farthest distance from the Sun, of 2.28 AU. This takes it from just past the orbit of the Earth to well outside the orbit of Mars. The original mission plan was to orbit a probe around the asteroids before impact. This probe would have been built by the European Space Agency and been called the Asteroid Impact Monitoring Mission, or AIM. The combined mission would have been called IDA, for Asteroid Impact and Deflection Assessment. The Europeans would have launched AIM in October of 2020. It would have targeted the Didymus binary asteroid system. The smaller one is sometimes called Didymoon, by the way. AIM was equipped with a high-resolution imaging system and would have gone into orbit around the target asteroid, imaging the surface in high resolution, and sending the images back to Earth by laser communication. It would also have high-resolution radar to see below the surface, and an infrared imaging system. The infrared imager would collect any infrared light reflected or emitted by the surface of the asteroid. This can help us understand the composition. AIM would also have deployed a small lander. The lander would have come down to the surface fairly gently, and would have emitted a radar signal that could be recorded on the other side, a sort of radar CT scan, so we could know the interior of the asteroid. AIM would have then deployed 2 CubeSats. These would have taken up station near the asteroid to help record the impact. But this didn't happen. The AIM monitoring mission was canceled by the Europeans. The Americans went ahead with their part of the experiment, and DART is scheduled to launch on a Falcon 9 Block 5 from Vandenberg Space Force Base on the 24th of November of 2021. Rockets launched directly south from Vandenberg to go into a polar orbit. The DART impactor, sent by the Americans, will come in at full speed, 6,600 meters per second. At a mass of 500 kilograms, it will indeed hit with a force of 3.3 million newtons. But AIM won't be there to see it. The DART does indeed have a Draco camera system. Draco stands for Didymus Reconnaissance and Asteroid Camera for Optical Navigation. Draco will help us determine the impact site as DART comes in. And DART has now been equipped with 2 CubeSats of its own. These are 6-unit CubeSats with a mass of 14 kilograms, built by the Italian Space Agency and called Licia Cube. Licia stands for Light Italian CubeSat for Imaging Asteroids, and is probably pronounced Licia. 10 days before DART impacts, these CubeSats will be deployed at a velocity of 1.1 meters per second by a spring-loaded mechanism. And with the help of onboard propulsion, these 2 cameras will be 3 minutes behind DART to capture scientific data and imaging of the impact results and send it back to Earth. This type of research is critical to human survival. At some point, the Earth, or an off-world colony, will be threatened by an asteroid impact. If we have our Starship threat detection system working, we should detect it in time to take action and avoid catastrophe. The DART mission is vital to understanding these impacts, and is a clear example of NASA at its best. Now let's watch NASA explain how we will observe this impact on the 26th.
This is Lowell Observatory. Lowell is one of many observatories around the world that will be observing the DART impact, NASA's first ever planetary defense test mission, to see how much a spacecraft impact can deflect an asteroid in its orbit. This is where Pluto was discovered, and we are still doing research in all areas of astronomy today. So let's go check it out. This is the Pluto telescope, the telescope that was used to discover Pluto almost 100 years ago. So here we are at the Clark telescope. This is where Percival Lowell sat to observe Mars. Let's head on over to the Lowell Discovery Telescope about an hour south of Flagstaff, which is where we are going to be collecting data for the DART mission. And the reason we're all the way out here in the middle of this forest is that we have really dark skies here. And this is the Lowell Discovery Telescope. This is what a 4.3 meter telescope looks like. This is what we will be using to study Didymos and Dimorphos in the days and weeks after DART impact. The DART spacecraft will be hitting an asteroid called Dimorphos. It's special because it's a binary asteroid, which means a satellite around a larger asteroid called Didymos. And DART will actually be hitting Dimorphos. And what we will be measuring is how much DART changes the orbit of Dimorphos around Didymos. So this is an important test for planetary defense mitigation strategies in case we ever have to do this for real. The Lowell Discovery Telescope is one of many telescopes around the world which will be used to study Didymos and Dimorphos. It's really a global coordinated effort. And what we're looking at here is a large 4.3 meter primary mirror that's in the middle of the telescope tube here. Up at the top is a secondary mirror. The secondary mirror up top there is what is focusing the light down onto the instruments and allows us to take images with the camera that's located down at the bottom. This is maybe one of my favorite hidden rooms at the telescope. We're like standing inside the telescope, underneath the telescope, 100 tons above your head, held up by this and this, which is cool. It's sort of, as you can see, the highest peak around here, just over 8,000 feet. And come up here for sunset, because you know, the sun's setting right there. It's perfect. For DART, we're going to be collecting images of the night sky. And typically an observer would be here in front of one of these consoles, controlling the instrument and taking images like these as they're coming in off the telescope. DART is really a sort of before and after experiment. We need to understand the system before the spacecraft intentionally impacts, and then we have to understand what the outcome of that impact event is. As we watch from the Earth, Dimorphos will pass in front of Didymos and behind Didymos. What we will be doing with those images is measuring the brightness of Didymos in those images and looking at how that brightness changes. And those dips in brightness allow us to measure when these eclipses happen and measure the orbit period of Dimorphos. And so you have essentially a fixed star field here. All the white dots are stars of different brightness. And moving through this field is Didymos and Dimorphos, which again, we can't distinguish them as discrete points of light, but we have that small object moving through the field of view. So after impact, we will then be able to go back and start observing intensely, looking for those mutual events, those eclipse events of Dimorphos passing in front of and behind Didymos. And on each one of these frames, we're measuring the brightness to assess whether or not it's undergoing one of these events where Dimorphos is passing in front of or behind, and using those to determine the orbit period of Dimorphos around Didymos. This is such a cool experiment. It's such a singular experiment. Using the ground-based telescopes like this one and others around the world to watch the system and see how it's affected by this impact event, because that's really what's going to give us the answer to what did DART do at the time of impact. And that will be exciting to see how that evolves over the days and weeks following that impact.
It may take a while to determine the effect of the impact, provided all goes well and the impact occurs as planned. We'll be watching on Monday and hope for DART's success. But this is just the first step, as we said, in preparing a planetary defense system. Now we need to start building those really big spaceships with nuclear fission or fusion power, so that when our time does come, we do not go quietly into that dark night. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra.